Hello, I am Syed Billah. I am an assistant professor at the Pennsylvania State University. I'm presenting our work Tilt Explore, making tilt gestures usable for low vision smartphone users. This work is done with Farhani Momtaj, who is a graduate student at Penn State. A quick overview of our work. Low vision is broadly defined as a vision impairment that cannot be fully corrected even with glasses, medication, or surgery. People with low vision interact with smartphones via assistive technologies like screen magnifiers. Screen magnifiers provide built-in, multi-finger, multi-touch gesture to pan and zoom on screen content. Between panning and zooming operations, panning is done more frequently than zooming. In this work, we exclusively focused on panning gestures. To use built-in panning gestures, low vision users need to engage their both hands. They need to hold the phone with one hand and drag the magnified content with 2 or 3 fingers using the other hand, as shown in these pictures. This interaction is cumbersome, tiring, and error-prone. Our paper addresses these issues with built-in panning gestures. Our contribution is Tilt Explore, a tilt-based, usable, single-handed panning technique for low-vision smartphone users. The design of Tilt Explore was informed by a study with 12 low-vision participants, and the final prototype was evaluated by a second study with 16 low-vision users. Tilt Explore adapts low-vision users' interaction behavior. Compared to built-in panning gestures, it is significantly less error-prone and more efficient at lower magnification scale. Now I will demonstrate how Tilt Explore works. This is an unmagnified screen. After magnification, a low-vision user activates Tilt Explore by resting one finger on the screen for some time, like 800 milliseconds, as shown in this video. Content gliding under their fingertip automatically gets selected. The system provides various audio haptic feedback. To deactivate Tilt Explore, the user simply lifts their finger off the screen. Here is a longer video.
I really like, here we go, where's baby's fatty button?
Now that we know how Tilt Explore works, let's talk about its design process. Drawing on the large body of tilt-based research, we first identified key factors influencing the performance of tilt input. These factors are as follows. We considered tilt rotation along x and y axis, 30-degree max. As for tilt gesture delimiter, to indicate an intended tilt motion from an unintended one, we considered 4 different delimiters. Double flip, where the user rotates the phone along its long side so that the phone screen is away and then put it back quickly, as shown in here. Throw gesture, where the user abruptly moves the phone back and forth by a small margin while facing the screen, as shown here. Press and hold a clutch button, where the user pressed and hold a clutch button for the duration of tilt. As shown in bottom right, this clutch could be an assistive touch-like button on iPhone or a floating button. With a toggle clutch button, the user presses the clutch to turn the tilt gesture on and presses it again to turn it off. For panning control, we chose velocity-based control, where the movement is proportionate to the amount of tilt per second. Finally, for the transfer function, we use Hinckley's transfer function, where panning is restricted to either x and y at a time. Based on this initial parameter, we developed a prototype of tilt to pan on Android and conducted a formative study with 12 low-vision participants. As for the task, we asked them to execute tilt delimiters 5 times each, find a target in 2-dimensional grid, and read a row in 1-dimensional layouts. We found that double flip and throw delimiters were the least favorite because the visual flow is interrupted and the users lost their context. Toggle clutch button was not favorite either because the user forgot to press the clutch again to stop tilt motion. Press and hold the clutch button was okay, but the floating clutch button was hard to see or locate. So the participant recommended touch and hold anywhere on the screen as the tilt motion delimiter. We also learned that a single-handed panning gesture was not a priority for some participants, but an alternative usable panning gesture was. As shown in this figure, some participants brought the phone very close to their eyes, leaving little space between the screen and their eyes to issue panning gesture. So, tilt-based panning gesture was considered as an addition, not a substitution. We also found that when making panning gestures, not all 3 or 2 fingers touch the screen simultaneously, like here. The finger that touches the screen right before others registers an unintended one-finger tap event, causing accidental context switches. So, our tilt-based panning should prevent such context switches. We observed that when using tilt to pan, some participants tilted the phone along an axis quickly to create a mental scope, then gradually tilted the phone backward, causing the panning to pause momentarily before picking up speed in the opposite direction, as if they were buying some time to process visual content. This process looked like a wave of tilt motions. So we need to capture this phenomenon in our transfer function. Finally, most participants used a screen reader to supplement their screen magnifier, especially when reading text. So integrating screen reading features into a screen magnifier is recommended. From this study, we can conclude that prior work on tilt-based interaction are mostly unusable for low vision users. Based on the recommendation and our observation, we revised our prototype as follows. First, we borrowed touch exploration feature from screen readers that makes touching the screen risk-free and enables limited screen reading feature into screen magnifiers. So our final tilt gesture delimiter is touching and holding anywhere on the screen with one finger for some time, like 800 milliseconds, to turn on tilt to pan, and lifting the finger off the screen to turn it off. This process, as shown before, is right here. We also provided various audio haptic feedback to notify different events, such as when hitting an edge or a boundary. Finally, we revised our transfer function to incorporate waves of tilt motion. To that end, we introduced a notion of dynamic reference that updates in every lambda seconds to capture the orientation of the device at that time. Pictorially, this is how it goes. This is our static reference, the blue line. At time t, delta theta s is the tilt angle with respect to our static reference. So this is the tilt angle with respect to our static reference. Let's say time t is a multiple of lambda, and the dynamic references is also set at time t. Now, this green line is our dynamic reference. At t plus 1, if the user tilted the phone backward a little, then delta theta d and delta theta s represent the tilt angle with respect to dynamic and static references. So these two. Finally, our ultimate tilt angle is a linear combination of these two, where eta is 0.8 and lambda is 5 seconds. Our hypothesis was the performance of Tilt Explorer would be as good as the built-in panning gestures, if not better. We conducted a summative study with 16 low vision participants, 10 males, 6 females who were around 50 years old on average. The study was a within-subject design with 2 conditions, baseline and Tilt Explorer, and 2 tasks per conditions. Task 1 was a visual task, which was finding a book in a 4x4 grid. Here is before magnification, and this is a magnified view. Task 2 was a reading paragraph, unmagnified view, the magnified view. We found that participants used almost 80% less panning gestures with Tilt Explorer. In addition, the number of accidental taps or context switches was reduced by 95% with Tilt Explorer. These reductions were statistically significant. Regarding task completion time, the participants took slightly more time to complete visual searches with Tilt Explorer, but this difference was not statistically significant. Interestingly, participants who needed lower magnification, such as less than 4x, took significantly less time with Tilt Explorer. In practice, low vision users are likely to take less time with Tilt Explorer if the recovery time from accidental context switches are considered. For reading speed, we conclude that panning is not suitable for reading tasks. We recorded the highest reading speed of 44 words per minute, which is still not comparable to that of people without vision impairment, whose reading speed is around 250 words per minute. In terms of subjective feedback, participants who did not have an age-related conditions rated Tilt Explorer highly favorably. The analysis of NASA TLX scores of both conditions revealed that the difference of overall scores was not statistically significant, except for those who were 45 or under. With Tilt Explorer, the physical and temporal workload were increased significantly, but the frustration was reduced significantly. In conclusion, Tilt Explore is a usable single-handed panning technique for screen magnifiers, although most low vision users are likely to use it manually, and they are likely to consider it as an addition to built-in panning gestures. Tilt Explores utilize screen reader's touch exploration mode. It reduces accidental context switches during panning. The risk of accidentally turning it on is low. It can work seamlessly with a screen magnifier or a screen reader, although it can be a standalone mode by its own right. The efficiency comes from the dexterity of human wrist movement. Unfortunately, this dependence is also a limitation for Tilt Explore because low vision users often develop difficulty in tilting due to age-related conditions. Finally, low vision users who need lower magnification, such as less than 4x, and who are 45 or under are likely to benefit from Tilt Explore the most. Thank you.